Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much for coming back on time. We will go ahead and try and stick on schedule, and I'd like to turn it over now to Tony Williams to come talk to us about ChemSpider and other things going on at Royal Society of Chemistry.
Is this active?
Should be.
Okay. So first of all, thank you for the invitation. I love it at this part of the world. I actually got engaged out here a few years ago, and life has been great since then. I'm going to tell you a little bit about a pragmatic vision. So the people who know me would say that I just get down to it. I don't let anything stand in the way, and I'll do silly things that are against most recommendations. This is an example of that. This is actually a hobby that started off in a basement. Started off with a vision of building a structure-centric community for chemists. So I was watching what was going on with PubChem and things like e-molecules and databases online of chemical structures. And I was working in a company where we dealt with prediction algorithms for structures. We drew them, we databased them. I was working a lot of hours, and I decided to do something that was creative and fun. Hard work is not always creative. That's one of the challenges of having a career. So started off with a hobby project in December of 2006, and it was to integrate chemical data on the web. I liked what PubChem was doing, but they were very focused on dealing with assay data. I started having a concept about how could you do something Wikipedia-like around chemical structures specifically. So we integrated chemical structure on the web. That was the vision. Make it a hub to information, because the web is just covered in information about chemical structures, but there's no easy way into it and out to all of the data. We wanted to provide access to structure-based algorithms. So because I was in the world of cheminformatics, I knew a lot of people who were building algorithms and might be willing to share them. We wanted to let chemists contribute their own data, because there's a lot of data that get generated that sit in notebooks, sit in pads. They never find their way anywhere. So let them put it somewhere. Wikipedia is not the place for everything that's getting run, because it's an encyclopedia. Google spreadsheets could work, for example. It certainly ends up in Excel spreadsheets and Word documents, but then it gets limited. It doesn't get shared. So we wanted to share it. And we wanted this ability to allow the community to curate and correct data. Because, of course, everything they write about Tom Cruise on the web is true. So therefore, everything about chemical structures on the web must be true. There's so much stuff out there, it's scary how bad it is. Chemistry Online today, where is it? I'm not going to read this list out. It's all there. It's encyclopedias and property databases and drug discovery data and publications. Chemical structure information is all over the place. The searches on the internet today primarily limited to text-based searching. That's probably what you would know about if you were trying to search for information about a particular compound. The data are certainly dirty. I'll show you some examples. It's very difficult to figure out what's good and what's bad. You just don't know. Who can you trust? Who are the authorities out on the internet? And too many searches are required to resource data. You do a search on any of the search engines that's a text-based search for a chemical compound, and you can get anywhere from a few tens of hits to millions. And now how do you figure out what's behind it? So humans do not want to deal with lots of interfaces. They actually want to deal with something that's rather simple to use. That's why they mostly go to a single search engine today. They want as few interfaces as possible, but to get as much integrated information as they can. What would the future look like? And actually, how far away is the future? Because it's coming very, very quickly. The semantic web for chemistry is in place. That's our future. Whatever this thing, the semantic web, is going to end up to be, it's going to be there. Crowdsourced contributions, well, crowdsourcing is here. When you read Amazon book reviews or movie reviews, I mean, that's the crowdsourcing right there. Wikipedia, that's crowdsourcing. Chemists will be searching the internet based on structure and substructure, not just text. There's no reason they shouldn't work in their own language. Chemistry articles are indexed and searchable, both text-based as well as structure and substructure. Why not? It just makes sense for a chemist. Again, reduced number of searches. The data are integrated, so if you want to find all the publications about a chemical, that's easy, and all the patents, and where to buy the chemical, and why not all the analytical data, and all the melting points, boiling points, and properties that Jean-Claude and his group are putting up. Why not? Makes sense. And then we're going to be in this world of open access and open data. Peter's almost certainly going to talk to you about open data. He's a better person to do that than me. This is coming. In fact, in many ways, it's already here. We're just not naming it open data. Classical business models, they will have to change. So we had a vision, and we went off to get it done. In March 2007, we went to an International Chemical Society meeting in Chicago, and we'd released this searchable structure database online. We bought one computer, and we built two with our hands from a company called Tiger Direct, buying a motherboard and hard drive and chips and throwing them together. We plugged it into the cable internet that serves TV signals and voice over IP, and started letting people do searches. We seeded it with 10.5 million structures from the so-called public domain. We sourced them from PubChem. We released it with structure and substructure searching, and it went live. June 2007, a few months later, we realized that the data that we'd released out to the internet was very dirty. That just in our lookups, we were finding a lot of errors. So we had to figure out how to make that clean. Well, 10.5 million structures with maybe 20 to 30 to 100 names, lots of properties associated with them, leaves you open to a whole lot of data issues. So we needed the crowd to help us clean it. So we put on a curation layer. We said, okay, 10.5 million is a good start, and we will aggregate more data, but we'd like you, the scientists out there in the world who are using our system, to add your data. You might not want to publish it in a classical peer-reviewed sense, but you might want to share information, so why not? So we added on a deposition interface, and so it continued. This is the world of search engines today. This is what people are used to. Most people are working with a single box that says, enter something to search. In the world of chemistry, you can have chemical names, aspirin, erythromycin, vancomycin. Those are very common types of searches. But then we have this thing called smile string, which is a way to represent a chemical structure. So we let you paste a smile string. We also have things called registry numbers, and those exist in registry systems such as the Chemical Abstract Service. We also have INCHIs. How many people in the room have not heard of INCHI? Okay, I will tell you a little bit about INCHI shortly. Let me swap over here to, I can figure this out. I'm trying to figure out how to get to the live internet here. Oh, here we go. So, this is ChemSpider, chemspider.com. Free to everybody to access, no charges to use it. If you search cholesterol, it's about 0.02 of a second to search it. It's running now out of Cambridge because ChemSpider actually worked and the Royal Society of Chemistry came and acquired it. It's a chemical structure, here's some properties, here's a systematic name. This is a smile string that represents that molecule. These are INCHIs. I will tell you more about what they're about shortly, but they are text strings, alphanumeric text strings that represent this molecule. There's a link to a Wikipedia article, but it doesn't make sense for us to pull the entire Wikipedia article and database it because it's changing all the time. People are rewriting these things and adding information, so we let you read it. Here's a list of patents. If there's a new patent available, then it's going to find it on this search. These are linked out directly to patents. Down here we have a list of articles. These are articles on PubMed. If PubMed is publishing multiple articles a day, this is a web service hit on PubMed. So if there's a new article there, it will show up. We don't cache this information for longer than a few hours. So a new article on cholesterol will show up here. And this is only a subset of them, by the way. You can always click through to see the full list. Here's a list of supplemental information where there's additional information about it. These are articles that haven't found their way to PubMed because not everything goes to PubMed. If it's not about medicine, then it doesn't necessarily belong there. Here's some properties with direct links. You can see down here we have the actual link out to the original data source who said that is the particular value. and you can click through and you'll find your way out into the original data source. Notice we've got melting points with units and without units. That's because of what the data source provides. Here's a whole set of chemical names, and there are a lot more. These are all names for cholesterol. These are validated names, the bolded ones. These are not validated, i.e. there's no highlights on them, they're not bolded. These are different types of database IDs. Here's some database ID. There's a long list of database IDs if I'd enabled it. It's just too much for this particular page. So we've got all of this information showing up on ChemSpider. 0.02 of a second. It's got 23.5 million molecules today, and it's linked out to 300 data sources. Let's go back here. So one of the other things we have on here are live data, so spectral data that gets submitted. We don't run any spectral data. We can't afford a $500,000 spectrometer, so we let anybody who's running the data submit it to the system. It's fully interactive, similar to what Jean-Claude was showing. This is an open source applet where we allow people to zoom in and download the data if it's open data. The data source is where we aggregate the data from. Where possible, we link out to them directly. So we're building, if you like, a link farm. In this case, this little icon here says it's a chemical vendor. If you want to go buy the material, you can go buy it. If you hover over the hyperlink that goes out, then it will take you a snapshot of what's over on that page. In this case, you get a material safety data sheet in Chinese, English, and Korean for cholesterol. Some of these MSDS sheets I've seen up to 16 languages represented. It's not sitting on our server. It's a link out to somebody else's server. And we have 300 data sources that we're linking out to now. This is the Environmental Protection Agency, EPA, DSS Tox, a metabolome database, Food and Drug Administration. We're aggregating all of the data. When we do that, however, we've been hitting some interesting issues I'm going to tell you about. This is an example of how extensive this data can get. This is KEG, Kyoto Encyclopedia of Genes and Genomes. These are massive metabolic pathways. I mean, just massive. You're scrolling around the page, finding your way around. In this case, we clicked in through the structure of aspirin, which is just up here on the left-hand side. Again, we can't host all this data because it's changing on everybody's website. Patterns and structures. This is actually the new way we're going to be showing it in a couple of weeks, where you can see US Patent Office, EPAB, European, Japanese patents are all there. And a new way we're going to be showing articles. I showed you the simple way to search a name, a chemical name or a smile string. In reality, chemists don't want to work that way only. That was magic. Because if you have a chemical that is named in 300 ways, how would you do that text search? You'd have to know all 300 names to do it. So you have to disambiguate through the structure in most cases. So we allow you to do structure searching. We allow you to do substructure searching. We allow you to search based on properties, the presence of certain elements, the absence of certain elements. We allow you to search on molecular weight range, and on and on and on. Incredible layers of complexity that you can search by that people are using, but most of us are used to Google and Bing type searches. So most chemists come in and search based on name. Once you come to a ChemSpider record, you're sitting on a structure that is linked out to many things. I've shown you some of them: publications, analytical data, related reactions, Wikipedia, patents. The question is, where should it stop? How big can this go? When you have a structure-centric hub, then essentially it's all about what do you want to plug into this. And it can be blogs and Wikipedia, wiki links, etc. These are typical questions that a chemist would ask in their language, standard English. What is phenolphthalein? What's the structure? What does it do? What's the side effects of it? What's the toxicity of it? All of those questions there can be answered today by ChemSpider. And it's getting better and better and better in terms of what we integrate. What's a compound? The top graphical depiction is a chemical structure. The one below it is a CAS number. The one below that, oxymonum, is a trivial name. The one below that is a systematic name. They're all the same. They're just different because they're different ways of you have to label things. If I say oxymonum, I'm probably a pharmacist. if I showed you the picture of the molecule, then you wouldn't know what to do with it unless you're a chemist. So that's why we have to work in these different interchanges. So because we're a structure-centric hub, and we're linking out to the internet, and we're bringing together patents and publications, and all of the data that's out there that we can link, we're now making a structure-based, searchable internet. The question is, how good can it be? This is the type of linked data on the web that is showing up now with different services. So DBpedia is out there, CHEBI, which is a chemical entities of biological interest from the European Bioinformatics Institute. We've got PubChem, we've got PubMed. All of these things are linking together with specific links, such as names, but this INSHI has shown up. I'm going to show you a little more about that. Aspirin, I'm sure most of you have heard of aspirin. Taxol. Anybody here not heard of Taxol? Okay. Oh, interesting. So it's a Bristol Myers drug. It's rather difficult. It was isolated from the Pacific yew tree bark. It's a very powerful drug. It's a natural product. It's very complex. Where would you go find what the chemical structure of that is? If you went to Wikipedia and looked for aspirin, it's very small. It's easy. It's correct. The original structure of Taxol on Wikipedia was incorrect. This one down on the left-hand side, you probably know that one. Nothing personal.
Why would I know that?
So a little blue pill from Pfizer. You've got to question everything online. Why are you glowing? So dhmo.org. So this is a nice little website. Dihydrogen monoxide. You die if you ingest too much of it, long periods of immersion, and you will also die, because that's called drowning, because indeed, dihydrogen monoxide, 2 hydrogens, 1 oxygen, is water. It's a hoax. It's a wonderfully well done hoax. I suggest you go read it. It's so well done, actually, that if you read the Wikipedia article, you hear about the politicians that tried to get DHMO banned from industrial processes. True stories. Chemistry on the internet is messy. You can imagine what might happen there that might get rather messy. It's probably methane. For every action, there's an equal opposite reaction. He should be flying this way, right? So what's methane? Wikipedia, simple organic molecule, 1 carbon, 4 protons. That is correct. Wikipedia article has been validated by numerous people. If you go to PubChem, which is a government database housed by the National Institute of Health, that's the correct structure of methane. It's actually labeled as charcoal. Now, if you throw methane on a barbecue in the summer, rather than charcoal, you'll get the type of cooking effect you were seeing with the cow, but not quite what you would want. If you look at the long list of names that are associated with methane on PubChem, you will see diamond. That's not a particularly good one, because diamond is not exactly a gas, and you could imagine handing over a gold ring with, it's not the right thing to do, really. Graphite, also not methane and also not diamond. Buckyball is also listed. This is a database of chemistry. It's from PubChem. It's an excellent platform. PubChem is a wonderful platform for data. However, they're not responsible for curating it. As a result, data have been showing up on PubChem for the past few years, and it's kind of public domain, so people have been taking it and putting it in their own databases, and now you have this proliferation of errors all over the place. It's actually quite shocking. Is that the right structure of vancomycin? Now, only some of you are chemists, but even those of you who are chemists, I would not imagine that you could check every stereochemical center there very easily. That's a rather complex molecule. I'm sure a number of you have had vancomycin at some point. That is the correct structure. If you search PubChem, then you end up with, I think, 3 or 4 pages of molecules called vancomycin. People are taking these data into models. They're building models of prediction. They're using it to resource information from which one's vancomycin? Which one should you use? Actually, the structure of vancomycin is primarily an assertion. It comes from analytical data. It comes from who says it's what. We've just released a publication that shows how many articles are published with incorrect chemical structures. And it's absolutely shocking. Good science to the best of their abilities, but still a lot of errors. So we've cleaned up a few hundred of late. We had inherited all of those errors about vancomycin onto ChemSpider, plus many others from other sources. So we actually had to go clean it up. You do a search on ChemSpider today, there's one vancomycin. It took 3 days of multiple email exchanges with the scientists at the EBI to figure it out. Now you go to our article and it will tell you why we say this is vancomycin. Direct links to original publications. One would assume that experts would get this stuff right. This is a web page about harmful algal blooms. That's domoic acid, which kills people. You get shellfish poisoning. You would assume that's correct. In fact, it's incorrect. Every stereocenter on that molecule from the experts is wrong. The bottom right-hand side with the red arrow is domoic acid on Wikipedia, also wrong. Top right-hand side is the structure of domoic acid from the American Chemical Society's C&E News article, also wrong. Do you see a similarity between the C&E News picture and the Wikipedia picture? That's because C&E News are taking data from Wikipedia directly. Wikipedia is being used as an encyclopedia and an authority. One would hope in the future that you could trust all of that data. I believe you will. You will be able to do that. Domoic acid's cleaned up now. We've been working on curating every chemical structure that is sitting in Wikipedia. We've checked every stereo bond, every connectivity. We've cleaned up lots and lots of errors. This is the correct structure of domoic acid on ChemSpider. The INSHI is a way of representing a structure, as I said, in alphanumeric text. So here you see a couple of examples. It has formula in it. It has isotope details. It has stereo layers. That whole string there can represent that full molecule. It's a very, very good way to encode structures to link together on the web. The problem is, search engines will truncate very, very long strings. So if it's a very, very big complex molecule and you try to search it, it will just drop the end off. So now you're stuck. So they had to come up with a way to make that a little more able to happen on search engines. So they built a hash that goes in. An SHA 256 hash, you take the molecule, you create the INSHI string at the top, you convert it to a hash, and now you have a fixed format for that molecule. There's two issues with that. One is you cannot go from the hash directly back to the molecule. And you also cannot go from the hash back to the string. You can only do it by doing a lookup. There's no way to reverse that hash. So what do? This is Taxol, now all the way back to that Pacific yew tree bark natural product. As you can see, rather complex. Below it is the string. Again, rather long, and below it is the hash. If you search across the databases on the internet for Taxol, you will find different hashes. There are 3 different hashes for Taxol. 2 of them are the same structure. 1 of them is different. And yet the 3 hashes are different. Why? Because you can have different settings when you generate the string. So that was a problem. So what they came up with was a way to create a standard INSHI. It's a standard set of options that will always produce the same outcome for any of the databases as long as the input is the same. The molecules have to be the same. Taxol was different by only 1 stereocenter. That's 1 position in the molecule. Does 1 stereocenter matter? Here we have 2 molecules differing in 1 stereocenter only. Anyone know what that molecule is? Thalidomide, yes. 1 stereocenter does matter. That's what 1 stereocenter does. So, who says what Taxol is? That's a challenge. It's assertions. If you look across most of the publications that are out there, many of them have got the structure drawn incorrectly. Timelines change, so a molecule published can be revisited a year later, and the structure has changed. The public data is full of these errors, and yet chemists would love to have a resource that they can trust. And the quality source today is the Chemical Abstract Service. But it's not easy to access. It's expensive to access. You have to pay for the license fees. This is vancomycin, the correct structure of vancomycin. Wouldn't it be nice to be able to find all representations of vancomycin on the internet? Well, now we go to this standard INSHI key. if there are databases being built, if there are patents being issued, if there are publications that are being written, where the structures that are contained within them have standard INCHI keys associated with them, you should be able to go search. So what we've done is we've put this directly on ChemSpider and said, if you find vancomycin, you want to find across the internet what goes on, you can click on the first part. This piece right here is the skeleton of the molecule. If you include this part, so you click on this part, then it includes all the stereochemistry. With all of that complex stereochemistry, I would always suggest you search in the skeleton, because people mess up stereochemistry rather easily. So what do we get? If you search the full molecule for vancomycin, so clicking on the second part of the string, you find 4 hits only. 2 of them are on ChemSpider. One of them is on PubChem, but don't forget there's 3 or 4 pages of them. So it finds one structure out of many. And then it finds something else on the chemical register. Vancomycin is a very, very common compound. So I would expect more than 4. So if I search the skeleton, I find 104. I find 100 more. And they're all called vancomycin. These are all sitting on public compound databases. The top one is highly curated, and it's different. So the internet is a mess. Somebody has to take the responsibility to try and connect it up and clean it up and feed all of the information back. By the way, when we've made changes to the database, when we've found errors, we communicate them back to the original sources, and literally 95% of the time, they don't make any changes at all. The screenshot I showed of PubChem with charcoal and methane has been there for 3 years. I've given the public presentation 30 or 40 times, and they don't change it. There has to be some changes, I think, in there. This is something called the INCHI resolver. Because a hash needs to get back to a structure, you can only do it through a lookup. So publishers are starting to layer INCHI keys onto publications. However, you can't convert the INCHI key to the structure. So we've had to build a resolver so you can search an INCHI key and find out what the molecule is. It's a public resource. These are the people we're depending on to grow the resource, to link in more information. Scientists, students, retired people. We've got retired curators running on ChemSpider today from all over the world. This is a curation screen. It shows you some of the edits that have been made and suggested. Anybody in this room can come to ChemSpider right now, suggest an error, and click on comments and tell us what you think is wrong. We have a gentleman who's retired NMR spectroscopist in Germany, Heinz Kolschorn, second one down. This third one down is somebody in China. I've never met these people. These are just examples of people who are contributing to clean it up. Multi-level curation. So I showed you what methane looked like on PubChem. Here's a whole list of names that were removed from that list that came from PubChem. They're still on the database, but they've been scratched out. Citizens could become data sources. This gentleman, he's one of my colleagues from the Royal Society of Chemistry, but he's building his own data source on ChemSpider. So he's a little subset of 23.5 million compounds. He's got 72 of his own molecules. We're just having a discussion about you can have a vanity site on ChemSpider. myname.chemspider.com. It's a multimedia resource, so we host videos and MP3s. This is Theodore Gray blowing up titanium, making titanium. This is a University of Nottingham professor talking about titanium. When we build rich resources of structures with dictionaries of names now, all these trivial names, synonyms, systematic names, registry numbers, then what you have is the ability to use it for semantic markup. Peter, will you talk about Oscar at all? Yes, okay.
Very brief.
Okay. Peter's been working on a project called Oscar for a number of years. The Royal Society of Chemistry use it as the basis of their semantic markup. It means finding chemical names inside text, and it could be multiple other dictionaries. It doesn't have to just be chemicals. Finding them, labeling them, and linking them out. In this case, Project Prospect from the RSC gives you the ability to see the chemical structure directly on an article. It makes the data very discoverable. This is an example of marking up a Wikipedia article, again using an entity extraction system. You can see some names highlighted. However, it misses a whole set of them. Bacentin, phosphentouin, diltiazem, erythromycin. I mean, these are pretty common drugs, but it misses them because the dictionary is incomplete. So you have to depend on good dictionaries. We built something called ChemMantis. You have a spider, ChemSpider, so ChemMantis just made sense. By the way, ChemMantis is markup and nomenclature transformation integrated system. We tried ChemSquirrel, but we couldn't come up with it to mean anything. So in a couple of seconds, you can go in and cross an entire chemistry article, and you can find all the chemical names and link them out to ChemSpider, which takes you out now into the world of Google and Bing and publications and patents and chemical vendors. From an article today, you could figure out where to buy the chemical, all the patents about the chemical, all the PubMed articles about that chemical. It's all linked up now. It doesn't have to just be chemicals. It can be species. This case, we're linked out to Wikipedia articles about species, and it could just as easily be hardware vendors and software vendors. They're just dictionaries. So what would you want to link it to? Well, we go back to that list of things that we were doing on ChemSpider. Once you've got the link off of your publication and into ChemSpider, you've just made the entire internet linked by structure. What we're trying to do is help people get away from having to draw structures themselves. Nobody should draw cholesterol again. If we've got it right, let them reuse it. So those of you who know how to embed videos from YouTube, you just take a little piece of JavaScript, go to ChemSpider, find the molecule of interest, and copy the JavaScript code into your blogs and your wikis. JC's students do this all the time. They never draw the molecules anymore, as long as we have them on ChemSpider. So that's embed code. By using the embed capabilities and the web services we've built around Spectra, now they can play games. And if students are playing games looking at spectral data and they find errors, they curate our data for us. We now provide a game to clean up our data. Tricky. It's great. So you come along and you choose which molecule fits that spectrum. It takes you to the next one. 10 spectra later, we make it 3 molecules, and then 4, and then 5. Make it more and more complex, and the students that are playing the game win awards. It's very cool. Computers don't want JavaScript. They want web services to integrate things together, so we've provided them. We're linking out in many ways now. So Notebook Science, Open Notebook Science are using us. Structure drawing packages are using us. Software offerings from billion-dollar organizations like Thermo Waters, Agilent Brooker, they're plugging us into their systems. iPhone apps are linked up to us. What we don't deal with yet, materials. Materials are tough. You can't draw a connection table. You can't draw a molecule very easily. Minerals are tough, polymers, and we don't intend to manage proteins. That's done well enough by other organizations. We're just going to talk about open data, likely open source. We're going to talk about open access. So ChemSpider is not open source. I'm going to thank Microsoft for being very kind to us and giving us MSDN licenses. It all runs on SQL Server. And while we've had people suggest we run it onto MySQL, we could do that, but we can't deliver things as quickly as we need to by moving to MySQL. We're on a Microsoft platform. We use open source components. There's some great open source components out there. It's not an open access database, because open access in most cases is a publishing term. It's free. It's free to use. You can take data, you can use web services, but it's not quote-unquote open access. We don't assume copyright when you give us data. It's your data. We're not taking it from you. And then this question is open data. Open data has been an interesting term for a number of years now. Panton principles, we've already heard mentioned by Cameron. Peter's going to talk about them again. Who declares data as open? Everything that sits on ChemSpider cannot by default be open. It can't. And that's because we have organizations giving us algorithms, and if we gave all of their data away, we would harm their business model. We have a pragmatic position. We're going to serve as a community resource and provide value, but we can't make everything free because we're not allowed to. So it's free but not open. So what it is today, 23 million compounds, 300 data sources, 7,000 users a day, 500,000 transactions. While I've been sitting here twittering in the back, I've also been flowing data in, put 80,000 molecules in this morning that I collected in San Francisco yesterday. Grows daily. We're providing a platform that other people can use for their own needs. We have to keep cleaning. The data out there are filthy today. We've got millions of structures left to deposit, 6 million. We're now integrating RSC content. A publication gets published by the RSC with structures. The data goes into ChemSpider at the same time. So that's going to flow out there together. We'd encourage all publishers to participate if they want to. And this semantic web for chemistry, we are trying our utmost to provide one of the pillars to use. Long list of people I could acknowledge. I'm out of time already. Synthetic pages, for those of you who care about chemical reactions, we're about to release a public database of chemical reactions for others to contribute to. And this is my contact information, and the slides are already up. I hit upload 1 minute before I stood up to talk, so they're there if you need them. And thank you.
Perhaps just 2 questions so we can stay on schedule if there's any questions.
So all this is sponsored by the Royal Society of Chemistry, is it?
So originally it was running out of the basement and it was self-funded as a hobby. Now it's actually owned by the Royal Society of Chemistry.
And is that sustainable in the long term?
Oh, they've been around a long, long time. Yes, that's fully.
It's cost quite a lot of money to do this.
My best estimates of what it took for us to build it was about $25,000, and lots of sweat and tears. To sustain it, well, it's scaling. It's growing bigger. We have an IT team now that's second to none, really. There's 3 of us that are full-time employees. There are different ways that we can look at generating revenue from this, but it'll always remain free. We can do advertising and we can license web services. But the RSC is a charity. So they have a publishing arm and they have a charitable arm. So in many ways, this is a giveaway back to the community because they're a society that is a charity. So yeah, it's fully sustainable, really. Bill?
When you link out to a data source or to whatever you link from a structure, do you have a way of coping with broken links? Because a lot of the times they're going to break on you.
Yeah, link decay?
Yeah, link decay.
Yeah.
What about link?
Can you repeat the question?
Yeah, so Bill's question is when we link out to a particular from a data source out to a particular link, and if that breaks, what do we do about that? So we're building systems so that we can actually go through and monitor for link decay, but you probably have to check things 3 or 4 times because sites can go off for a day or a week type of thing. Right now, we don't have that fully under control at all. It's okay for publications because we use DOIs, so we depend on Crossref to do that. Wikipedia is unlikely to change its domain name very easily. But Jean-Claude Bradley, for example, I mean, tomorrow he might choose to stop doing open notebook science. It's very unlikely. I mean, we just heard the guy talk, right? But he's been kind enough to put up his entire archive on Lulu. So we just bought a disk for $5 and we'll set it up on our servers and all his links will be safe in our world. But chemical vendors come and go and things like that. So some of those links are going to decay. At which point we'll just disable them, really. So it is a tricky thing to do.
Very good.
Thank you.
Thank you very much. And we'll let Peter get set up here. I don't know about you guys. Basement of my house is full of boxes. I think I might have a couple of bottles of wine down there. This guy's changing the face of chemistry. It's unbelievable. It's a pretty amazing hobby. I would like now to hand it over to Peter Murray Rust, who is one of the signers of the Penton Principles and one of 3, I think, that we have here today, and to give us a presentation on, I think, a broad variety of topics of the work that he's doing in and around this field. Over to you, Peter.
Right, well, I'm delighted to be here, and I'm also delighted that this is being recorded because I don't use PowerPoint, and I don't know what I'm going to say, and I need to know what I've said after I've said it. So this, I think, is a very important meeting, that it coincides with a whole lot of things which are coming together in terms of a release of openness. And I'm also delighted to see lots of people in the audience who've known remotely, people like Bill Hooker and Heather Pivovar and so on, which is great. So you meet up there. I'm going to talk about open data. I'm going to go through quite quickly because I've got three things to announce today, quite apart from anything else. I'm going to say something about the Panton principles because Cameron didn't show the pub. I'm going to talk about Is It Open from the Open Knowledge Foundation, and I'm going to give a sneak preview of Chem for Word. So lots of things that I might talk about, and I will come back to those later and see if any of them I've missed. Linked open data is another word for the semantic web, another approach. And what is key here is both open and linked. And if one is going to have machines running over the web, there must be zero friction. And in my view, the biggest amount of friction at the moment on the web is whether you are allowed to use that resource at the end without having lawyers send you some sort of letter. So what I believe is at the moment we can only do linked open data if all the data are absolutely certified, completely open. And I'll say what I mean by that. It's actually very easy. It is if it has got an open data button from the Open Knowledge Foundation. So that is my full definition of open data. Rufus Pollock, Jordan Hatcher and John Wilbanks. Is John here? Not. Hi there, he is, right. Have spent 2 years talking about this. They have solved the problem for me. They've gone into huge amounts of detail about this. I just accept they've got it right. So I just go ahead and say this data is open. There isn't a difference between open access and open data. You cannot take open access ideas and relate it to data. You cannot take open source and relate it to open data. And almost open, freely accessible are very valuable, but they are not good enough for open data. Now, I want to talk about software as an agent of change. We've seen how we can get things out with crowdsourcing, with communities, with all sorts of ways of doing things. Software is also a major way that one can push ideas, because if everybody uses a piece of software and that software has got in it embedded a political philosophy or a social philosophy, then that will get out to zillions of people. I also want to say something about web democracy. Now, you've probably seen that the UK has torn its insides out over MP scandal and things like that. We do this very well in the UK. We agonise. But that agonising is a process of democracy which is being fueled by web tools. And I want to say something about what my society has done here. I also want to say something about a bottom-up approach. I've been one of the founder members of the Blue Obelisk, and this is a community which creates software, data and other resources with no membership, no constitution, no nothing. All that happens is it just meets from time to time and occasionally people get a Blue Obelisk. I want also to say something about text and data mining. I think understanding human natural language is going to be the next great thing in information. At the moment, Google, all the tools you've heard about at the moment can only recognize things if they understand single words or stock phrases, or if people have worked very hard to programming into a template. I think that when we start understanding what people communicate in normal language, there will be a big breakthrough in our use of information. And I want to say something about the fact that if you get the right system, it is near zero cost to build it. Now, Tony's talked about ChemSpider, near zero cost. I'm going to talk about Crystal, which runs at essentially zero cost at the moment. You can build very, very cost-effective tools in certain circumstances. And finally, I want to... How many people here are from the library world? Yes, I thought so. Right? Right, okay, well, I'm going to say something. Libraries are not doing enough to make data open, right? They are simply not putting their heart into saying, this data must be out there. I went to a meeting last year on electronic theses and dissertations, and I said, can I have your theses and can I data mine those? And I'm going to show you what data mining can do. And they said things like, oh, well, you've got to write to every author and you've got to send it in on this form and all this sort of stuff. That is not Web 2.0, it's Web 0. So you have got to find out how to get that data out there now when it's published. There are no qualifications, no nothing. Get that stuff out, because theses are the biggest resource that we are missing at the moment in science. Okay, a few people to thank. My own colleagues in Cambridge, I'll just leave it up there. I'd hoped to blog all this before I started, but I haven't been blogging for a little while. I will resume. These are the people who've done wonderful things there. You've heard about Oscar, you've heard about understanding chemical names. There's a lot of chemistry here, and I make no apology, because actually chemistry is the best subject to do the scientific web on. Then a whole lot of other people who've contributed here, and you're going to hear about our involvement with Microsoft, which has been tremendously productive. So let me just say something, show you a picture of a blue obelisk. Much of the software, all the software I use, is open source. It's not all written by me or my colleagues, but it is part of this ecosystem that this community is providing. Now, my view is this is enormously liberating, because it is not only inexpensive, like Zero, but it is also something that you can take and modify and innovate with. You cannot innovate with commercial software. You can innovate with free software, free as in speech. Right. So, I'm going to build this on a project which I've been very honoured to be part of, which is Richard Whitby's dialer molecule from the University of Southampton. Richard has got a grant from the EPSRC, one of the research councils in the UK, for a 20-year vision. It's not funded for 20 years, but the vision is 20 years, to build a system where machines can reliably, 100%, work out how to make a molecule and then make it, right? So that if you think this would be a good drug, or this would interact with some part of the body, or whatever it might be, you just tell the machine, go off and do it, and it will do it for you. So that's the goal. Now, I am running this, the strand, which is the knowledge-driven approach. And this ties in with the fourth paradigm, the idea that much science from now on is going to be knowledge-driven, what is out there already. So I'm going to show you how we get at what's out there already. That was very clear that people didn't want simulations, they didn't want cunning algorithms, and so forth. They wanted to know what was actually out there at the moment. So you've seen a lot of chemistry. I'm going to talk about reactions, not molecules. I don't know how many reactions are published, either formally or informally, a year. I'm guessing it's, in the low millions, something of that sort. Do you know, Anthony? Tony? Well, how many new compounds are published a year? It's over 1 million.
Depends what you mean by published.
In chemical abstracts.
I think chemical abstracts are doing different things now, because they're enumerating from patents, and they're throwing in
anyway,
millions.
It's an awful lot, right? It really doesn't matter. It's zillions, right? Okay. Many of these repeated, which is very good, because it takes us back to what Jean-Claude does about the fact that you don't always get the same answer each time. They come from 3 sources mainly: journals, theses, and patents. Journals we've heard a bit about. Possibly the gold standard and possibly not, but the main problem you have with journals is the fact that most journals in chemistry are not free. So there is Wiley's statement about this: copyright Wiley. Copyright on the tables, copyright on the molecules, copyright on the spectra. The ACS are slightly less laid back about it. What is important, a subscription to an SGM journal is an access to a database maintained by the publisher. In other words, all our data belong to us, right? Okay? What you have here is the real problem that large organizations want to own data, and there's little sign of that going away at the moment. So we have to develop agents of cultural change, which are a mixture of stick and carrot, and you've heard of some of them already, but we've got to put in place that future which will allow us to move away from this central gatekeeper control. So back to dial a molecule. What's a patent look like? Well, this is a bit of a patent. I'm guessing, well, I know this I know because I have a colleague who's working on this. He downloads approximately 3,000 chemical patents a year from the European Patent Office, and they contain about 100,000 syntheses a year. And we can read them all. So here is a typical chemical reaction. You've seen this sort of thing. Now, I'm not going to justify this, but our software, our natural language processing software, can not only recognize the chemical names in that, it can understand the language that the chemist has used. So it can work out who did what to which, when, and for how long, and so forth. It understands every word in that sentence, which means that we now have a complete capture of that type of information. The patent itself is enormous. It's 270 pages. That's one patent. No human can read that, if they're doing lots of it. So here's a thesis. Now, one of the great things about theses is that there's much more detail in them about what doesn't work than there is in the published literature. If you publish a journal article and you say, well, this didn't work, they'll reject it. If you publish a thesis and you don't say this didn't work, your examiner will be on top of you. So there's a lot more in the thesis which is there. So here you've got a bit of a thesis. This is actually one of our postdocs in Cambridge, Jürgen Harter, with Steve Lay. And here you've got a reaction. Now this reaction is, I'm going to show it. Right, now, anyone recognize, oh my goodness, you're not meant to see that yet. Right, that's a surprise. Okay, so here's this, right, anyone recognize the software it's being displayed in? Well, don't laugh because I'm going to click on that. How many people recognize that bit of software? Right, because that reaction is actually a partially intelligent object. And you can click on it and the reaction will burst into life. Oh dear. The server application source file or item cannot be found. Now what does that mean? That means that if you pay a certain vendor about $250, you will be able to read that reaction. And so what we have here is gatekeeping by commercial software. That thesis is crippled by the non-availability of software. So we have to do something about it. That reaction needs liberating. And the only way we can liberate it is to come up with open software which does the same thing. Wonder if anybody can see where this is going. Kill that one. No, I don't want to save it and so on. And I'll put that one just down there for the moment. So anyway, here's a typical example of a failed reaction. Was not isolable. Instead, something happened. In addition, it was a somewhat unexpected product. These are words which are called, in natural language processing, called sentiment. And so we're doing sentiment analysis on this. We're trying to find out, what the motivation was, what happened, and so forth. So now we come down to what can we do about it. So here's the question. We want hundreds of thousands of reactions. We want them for zero cost, and we don't want any trouble. Right, okay. So here's our first effort, and Cameron didn't show this, but this is actually the Panton Arms, and you can see the people. That's Jenny Malloy, who's a second year or third year Cambridge undergraduate. She's done a huge amount of effort on that. Some of the others you'll recognize, but here's Rufus, right? This is Rufus Pollock, the indefatigable progenitor and, and hustler in the Open Knowledge Foundation. So he makes things happen. There's John, and that's Jordan, isn't it? I think. Anyway, there it is. This is a historic picture. So that's the Panther. But also, we wanted to know not only is the data there, can we get the open data, but how do we know it's open? So here I went to something called whatdotheyknow.org. Now, this is the freedom of information in the UK. And if we go to this, and this is Right. So this is actually a website, whatdotheyknow.org, and I can request a message from any organisation who's required to respond by the Freedom of Information Act. And I've mailed the British Library. I mailed the British Library about why were the British Library charging for open access publications, which they were. Dear Sir or Madam, now this is there in public. I asked that question, and because my society have created this tool, everybody can read that. So you can go to this whatdotheyknow.org and see who's requested what of bodies which are required by UK law to respond. And in fact, I got this back, and somewhere in the middle of this, I've probably got the result of this. What I thought is that wouldn't it be nice if we did the same for publishers? Is your data open, right? Yes? No? Possibly. So we put together a tool which is called Is It Open? And I think what I will do here is probably go to another web browser. Here we are, this is better. So here we are starting to ask authorities, whoever they are, is your data open? So I have mailed David Wild and Christoph Steinbeck, who are editors of the Journal of Chemical Informatics. And here I mailed them early this morning. I'm writing to ask you about the openness of data published in Journal of Chemoinformatics, right? Now, it's an open access journal, CC BY, so it's algorithmically open, if you like, but I thought we'd start with the easy ones. And what we've got back, here we are, within an hour or two, the editor has replied, asking his editor, a technical editor, can we put an open data button on the Journal of Chemical Informatics? Because that button is the key to making data open. All we have to do is to get that button onto enough data sets, enough software tools. We put it into tools so that tools create an open data button, and then the problem is solved. So that's what I mean by software being an agent of culture change. Now, I'm going to show, just before I show, did I mention Chem4Word? Yes. Before I show Chem4Word, I'm going to say just a very brief thing about crystalline. This was a student project, a graduate student project built by Nick Day, and this is built by one person over about 9 months. And what this system does is it trawls every publisher on the web who publishes crystal structures, brings them down every night and aggregates them. Now, it can't do every publisher because some of the publishers hide their stuff behind firewalls. So it doesn't do Wiley, it doesn't do Springer, it doesn't do Elsevier. But it does Royal Society of Chemistry, it does ACS, it does the International Union of Crystallography. This, you won't be surprised to know that this wonderful software on both sides here came from the Blue Obelisk. Let's just go through and look at this data. And what can you see at the top left of that page? Yes, you can see open data. And when you click on that, it goes through probably in finite time. Well, it's gone through, I think there you are. So it goes through to the open knowledge definition. That is open data. A machine knows that it can use that data there for any purpose whatsoever. Now, of course, reading the literature in this way is actually a bit of sticking plaster. We ultimately want to create semantic data at source. We've heard lots of ideas here. We've got some projects in-house which are looking at that, but the most important one here is Chem4Word. So I'm going to show you Chem4Word. Now I'm going to just start off by showing, here's a bit of a thesis in ordinary Word, and you'll notice here things like bold numbers which don't mean anything. That is actually a reference to compound 155. We don't know what it is because it's about 50 pages elsewhere in the thesis. So it makes it incredibly difficult to read. So what we've done here, and I don't have time to talk about Lee and Pablo and Alex and Tony Hay and the others, is over a year and a half built a completely free open source add-in for Word. It fits into Word 2010, and if I now go to, here we are, this is it. Here's what it looks like. Now, this is the same stuff here, but you'll notice now that when we move over anything in here, it lights up. And there's a whole list here of all of the molecules in the thesis. So if I want to know where water is here, I can go there and click it, and it lights up there. This one lights up there. That one lights up there, and so on. Now, this means that we know at each stage in the thesis exactly what it is. So this is a tool of much greater power than the current tools for a student editing their thesis. So this is not only, if you like, going to cost zero, it's actually going to do more. And what we're looking at is ways in which the community can help develop it. Now, that's actually wrong. So what I'm going to show you is how we can edit it. We go into the editor. To do that, we have to have what's called a 2D structure. Now, notice here, you probably can't read it, C11H1804, but remember those three numbers, right? And we go to 2D representation, and here it is. So that's the molecule. I go to Edit 2D, and now I realize that those should be acids instead. So I click on that one. I'm not a very good clicker sometimes. And that is easy. There we go. And we'll put an acid on that one, and we'll go to that. And we'll put an acid on that one. Right? We'll save it. It tells us that some of the names have changed. It's inconsistent. So it's, Tony told you all about how names didn't relate to the right things. This is the sort of way that it happens. So this tool is able to tell you where your names probably don't relate to whatever. But now, if you look at that, that's gone up to C11H8. So what is it? It's increased the number of oxygens in that. So what we have here is we have a tool which is open, which anybody can download, which we hope the community is going to build new innovations in without necessarily our permission, which then becomes a way of creating this chemical semantic web. Finally, I want to say a little bit about two other projects. I think I started a bit late, so I will have two extra. The next one is actually probably the first example of a designed small part of the chemical semantic web. It's relatively straightforward to put your stuff out there. It's more difficult for 2 or 3 people to share various components of that. And this is the OREChem project, which is sponsored by Microsoft, Lee's program director manager, whatever. And he chose 4 participants here, Penn State, Southampton, Cambridge and Indiana University, and the whole is coordinated from Cornell with Carl Lugosi, who's developed a semantic web framework for academia which is called OAI ORE. How many people have heard of OAI PMH? Well, this is its sort of little sister or whatever, right? It's coming along. It will be very important. It is very important, right? So the idea here is that Penn State reads stuff from the literature, does some crawling, indexing, sends it down to Southampton, who then turn it into partially semantic form. That then comes down here. These little things are RSS feeds. It comes down to Cambridge, and we turn it into chemical markup language and RDF, send it to Indiana, and Indiana then do high throughput computing on this. So one of the outcomes of this will be that we can compute every molecule that comes out on the web, because there might be 1 million molecules a year, whatever it is. They might take, some of them might take a week. But what is 1 million weeks on today's computers? Almost nothing. You'll find places anywhere to do that sort of thing. And of course, some of the companies are very keen to try this out. The last thing I'll talk about what we're doing here is, because it came up in relation to things that Jean-Claude was saying, is the release of data which is not immediate. So Jean-Claude has got these categories which I hadn't heard about before. And let's talk about the category which is delayed. So category either complete or partial, delayed. Now, the trouble is if you delay something, it's awfully easy actually to do nothing, to say, I'm going to do that later. So what our system here does, and you don't need to know the details here, it's an embargo manager called EMMA, and it controls when something is released. So the idea is you publish directly into EMMA at the time that you do it. So it's immediate but hidden. That means that you can take the same philosophy whether you're going to ultimately release it at all or whether you want to release it immediately. This manages the trust between the different components in the system so that some of this, for example, goes into an internal repository. You'll see private atom feed. Atom, by the way, is nothing to do with chemistry. It's an RSS protocol. And so, again, open source, anybody who needs an embargo manager, and I suspect most of you are going to need embargo managers, that will be available. So I'm just going to come back and review over 1 or 2 minutes the things that we've covered here. I hope that I've made the case that if we are doing completely machine collection and analysis of data, then it has to be truly open data along the lines of the Open Knowledge Foundation open data button, because a machine cannot make the decision about reading lawyers' letters and licenses and things like that. So it's got to be completely open. We accept pragmatically that there will be many things which are not completely open. It does allow us in principle to come down to a granularity where you could even stick this on individual data items of some sort. We've come very clearly to the conclusion, and particularly Cameron and myself, that we want a very simple approach. An awful lot of time is spent in the open access community trying to work out what open access is. It's actually what you do in many cases rather than huge amounts of discussion about it. If you come to the end, which is CC BY, it becomes trivial. And I would strongly suggest all of you, if you've got open access material, strive however you can just to make that CC BY. It solves all your problems. You actually got time to do something else. I'm very excited about the power of web democracy, of building tools which will change culture. You've seen what My Society can do. You can ask questions of people. Organizations are going to have to be more responsive to public interest and so on, and that will cover all sorts of disciplines. And it means, I think, that the publishers are going to have to step up and actually answer some of these questions. Publishers cannot hide at the moment. We know one publisher who's taken over 2 years not to respond to a query. That's really not acceptable when they are charging academia huge amounts of money for the privilege of reading our material. I think text and data mining are going to be critical, but until we solve the legal problem, it's going to be problematic. We start with the bits that are easy. And I would therefore like to thank the organizers for inviting me. I'm very pleased to be associated with the Science Commons effort in this area, and also a great deal of thanks to Microsoft over the last 3 years, who have moved an enormous amount. When we started this project, there was no hint of open source. We are now at the stage where there is enthusiastic pressure from Microsoft to release this as open source, and we're really looking forward to this change in culture with freedom means innovation and involvement. Thank you.
Is Chem4Word open source at the moment?
Lee, actually, I think Lee, if you answer that question, it's probably a more accurate answer.
So we'll be releasing the beta for Chem4Word. It will be actually released. We've been working on it, kind of co-developing it over the course of the last year and a half. Be announced that we'll release the beta next month, probably at ACS. The beta will be made available open source. We haven't finalized the licensing terms, but it's probably going to be an Apache license. And then once at that point, we're going to hand it over to Cambridge, and Cambridge is going to take that project on and move it forward. And it won't be, we'll probably have a seat at the table, but they will be the benevolent dictator of the of that project moving forward.
Yes. And Lee is the 800-pound gorilla who's making this happen.
Thank you, Peter.
What is CC BY?
Right. Okay, this is a good time to go out on the web. So this is one of the great advantages of the web. We'll go out and see if we can find CC BY. I do have a slide, but it's actually quicker just to do this. Right, Creative Commons Attribution to Generic. It says you are free to share it, copy, distribute, and transmit it, and you're free to adapt it. And you must acknowledge the work in the manner specified by the author or licensor, but not in any way that suggests that they endorse you or that. So in other words, it is that you must attribute the source, and that's it. Right. It's wonderfully powerful. So, yeah? Sorry, was there another question?
You explain it to you first.
Sorry.
Yeah. Will there be a chem for OpenOffice?
Good question. We have two technical problems here. One is the question of language, right? So Chem for Word is written in C#, which is an open language, but is largely used on Microsoft platforms, right? Whether that would work in an OpenOffice environment, I don't know. Secondly, there are certain things which are called in OpenOffice, in Chem for Word, which are probably not present in OpenOffice, right? There is no reason why it couldn't be reverse engineered for OpenOffice. We are not funded to do that. I think, personally, I think it would be a good idea to do that if there is a need for it. Yeah?
You were talking about the embargo. What sort of time periods have people been talking about?
Well, normally it's actually until time of publication. So normally what a chemist wants to do, now of course we do have some problems here, but let me just go back to the picture of it. Normally what a chemist wants to do is to keep their data safe, know that at some stage they're going to do something with it. They don't necessarily know what they want to do. They certainly don't want it released before publication, because some publishers will actually then regard the publication as invalid and probably reject their next paper or whatever. It's actually quite a difficult thing to know when a paper has been published. A young researcher may very well read every issue of whatever, scan the web pages, but there's nothing that triggers this has been published, right? There isn't a place, where triggers come back to the author. So what I think Emma can probably do, although there's no immediate mechanism for this, is to respond to that trigger when something's been published. So this would also work for things like theses. So clearly when the thesis has been accepted and put in the library, then that's the time at which data might be released. So sometimes it might be 6 months, but it's more likely to be until such an event has occurred.
So are you talking about just the experiments that support the paper, or the associated failed experiments as well?
It's whatever we can persuade people to do. I mean, we have an approach in Cambridge where we have invested in a commercial electronic lab notebook, but we are managing independently our own NMR and X-ray data and so on. Now, it's my hope that all of the X-ray and NMR data goes into this anyway, right? There's a question as to who. The sort of problems you have in something like this is who owns it, how do you identify people? It's not actually trivial to identify people, authorities, groups, and things like that. So all of this is bringing out the problems in the human metadata here. The scientific metadata is straightforward. It's the human metadata that's different.
Are people ready for lunch?
I'm sure they are.
All right, thank you very much, Peter.